Welcome back, guys. Thank you so much for all the love that you have been giving me for the past few days, especially. We're continuing rate of reactions, and I'll be uploading more videos on tips and tricks for chemistry. So, today's video is going to be about the factors that affect the rate of reaction. It is perhaps the last video in the series of rate of reactions. We have skipped few minor details, but we're going to be completing the overall chapter superficially. So, let's talk about it. When we talk about the factors that affect rate of reaction, we should know that reactant particles always collide to make the product. In order for the reactant molecules to collide and make the product, there has to be two things that we keep in mind. The bonds in reactant particles break down while they're colliding, and the product molecules are made, so new bonds are made, new bonds are formed which are required for the product. We should keep in mind that these bonds may be different because the reactant molecules are breaking their bond and new bonds are being made for the product. The first thing for this to be achieved is there has to be a collision between the reactants. And we use the phrase of collision frequency, which means the number of collisions per unit time, especially per unit second. The second is that the reactant particles should have enough energy. And there's a threshold, there's a limit for that energy, and the energy should be higher than that limit. We call that limit activation energy. So just colliding is not enough, they should have energy higher than activation energy. Imagine these particles are colliding, the green one and the red one. If you increase the temperature, their collision will become faster. If you increase the temperature even further, their collision will even speed up because temperature means average kinetic energy. So if you increase the temperature even further, the kinetic energy increases and the particles collide more per unit second. So by increasing the temperature, higher temperature provides faster reactions. Why? Because higher temperature increases the kinetic energy of the particles. If you remember physics, kinetic energy is related to the velocity square. So higher speed of particles is resulted when higher kinetic energy is available. And when higher kinetic energy is available, it allows more frequency of successful collisions. It allows more collision frequency, which means more collisions per unit second. It's really important to say per unit second, or just the word frequency is enough. And when the frequency collision increases, it's a faster reaction. Another thing that we should keep in mind is that temperature allows more particles which have higher energy than the activation energy limit. So it increases the particle's energy, so more particles have energy which is higher than the activation energy. And now we should keep in mind that just colliding was not enough, they should have the energy which is more than activation energy. Imagine you have a graph with time on the x-axis and you're collecting some gas as a product on the y-axis. There are two different graphs with different gradients, but their final height is same. The red graph represents the reaction at 35 degrees Celsius and the purple one represents the reaction at 45 degrees Celsius. You can see the gradient or the slopes are different. The purple one has a higher gradient, so it's faster. The red one has lower gradient, so it is slower. But the final product is same. They may take more or less time, but the amount of product is going to be same amount of product because perhaps the amount of reactant was same. Another factor that we should keep in mind is the pressure. It affects only gaseous reactions. Over here, we should know that when pressure increases, the gases are squeezed. So the volume decreases and the particles come closer, so there are more particles per unit volume. You should keep in mind that we are talking about particles per unit volume. So higher pressure decreases the volume because it compresses it. And as a result, what happens is that particles are crowded. They become more closer to each other. So more particles per unit volume. You can't just say more particles. You're not talking about it in general manners. You're talking about per unit volume. And since more particles are there per unit volume, the frequency of successful collisions increases. We are not changing their energy over here. We are just making them crowded together so their collision frequency increases. They collide more times per unit second. In a similar graph, if you have two different pressures, the orange graph represents a reaction at a higher gradient and the red one represents a graph with lower gradient. So the graph with the red represents low gas pressure and the graph with orange represents higher pressure. You can notice that their heights are same. They are reaching the final y-axis, which means the amount of product is same. It is the x-axis which is different, so the orange graph becomes flat, becomes horizontal much quicker than the red graph. Red graph takes more time, which means it is slower. Another factor is the surface area of solids. It only affects the rate of reaction for solids. So surface area is only applicable when we are dealing with substances which are solid in nature. Higher surface area, which means powdered substances, have more exposure with the reactants. Higher surface area allows more frequency of collisions because more particles are now crushed, they are powdered, so they can react with the other substance really quickly. It allows more frequency of successful collisions. Imagine you have two beakers which have dilute hydrochloric acid in them. The other beaker also has dilute hydrochloric acid in it. In one of these beakers, you have bigger pieces of solid calcium carbonate. So these are large pieces of solid calcium carbonate, which is obviously solid. We know calcium carbonate is insoluble. We are adding it over here. And in the other one, you're having powdered calcium carbonate. So you have powdered calcium carbonate in the other one. The powdered one has more surface area. More surface area helps in faster reaction because more particles are exposed and they increase the collision frequency. So you will see bubbles of gas at different rates in both reactions. The one with lower surface area produces bubbles really slowly, but the one with higher surface area produces bubbles really quickly. These are the bubbles of carbon dioxide gas, we know that. But the rate of bubbles is also different because it shows how the speed of reaction is different over here. You see faster fizzing in one, slower in the other. The last is catalyst. Catalyst is any substance which decreases the activation energy. It is not increasing the energy of particles, but it is decreasing the activation energy limit. Each reaction has its own activation energy and catalyst decreases it. It provides an alternate kind of mechanism. It provides an alternate kind of route which has lower activation energy. So now particles with even lesser energy can have successful collisions. They can make the product. You're not changing the energy of individual particles, but you're decreasing the activation energy of the whole reaction. Catalysts are left unreacted after the reaction. It is a misconception they don't participate in reaction. They do, but they are left in the same position, in the same form as they began with. Imagine you have reactants energy and products energy, and reactants are on a higher energy, so it's a kind of exothermic reaction which is releasing heat. The enthalpy arrow is going downwards. The reaction follows like this. It increases from the red to the product, from the reactant to the product, which means that there is a kind of increase in the beginning, which shows the activation energy, and it has been represented by a green arrow. The green arrow, the hump, represents the activation energy because the energy goes very higher in the beginning. If you had a catalyst, the activation energy would decrease and you would have a graph which looks like the purple one. The purple one has the same reactant and product, but this time you have less activation energy. So with less activation energy, you're going to get the reaction at a faster speed. You're going to get the products in lesser time. So these are the factors that affect rate of reaction. I hope I'm clear to you guys. You can follow the upcoming videos at my Instagram. The link is over there. And you can also follow the tips that I'm going to be sharing in tomorrow's video. Stay tuned, guys. Thanks for all the love that you gave.